Okay, so we have to backtrack a little bit to review what I was starting last lecture, and also to review what you've read now. We have three related phenomena that we put under the umbrella of magnetic induction, and they're all clearly related to the magnetic field that is generated by a current carrying wire. So we have to see how this works. We'll set up a primary and a secondary. The primary has current flowing in it, that is charges with impetus that are inside a chart. In other words, it has parts that virtually have impetus and charges that are flowing in the wire. And there are three different things that you can do to induce current to flow in the secondary. And we're going to demonstrate that here in a second, but first I'm going to sketch them here for you. The first one is to push the secondary towards the primary, and that induces a current in the secondary. And notice the direction of the current. As the secondary gets closer to the primary, the current induced in the secondary and the closest part of the secondary is flowing in the opposite direction. And then we're going to study, of course, now the forces that are caused by this. But first there's just a current induced. The second thing is I could push the primary towards the secondary. Those are two different things that are going on, right? Keep in mind, those are two different things. In particular, the secondary is not moving in the second one. And in the third one, there we have it. We could increase the current in the primary. All three of those things would do the same effect. And so I want to demonstrate that to you. I have two coils here, wire loops, and there are a lot of turns here. So that enhances the magnetic field. If I did it with just a single wire like this, the effect is really weak. By enhancing, I can enhance it here. There's lots of turns, so I hope the camera can pick up on this and that you can see this. There's a lot. It's pretty thick here. There's a lot of turns here, and the wire here has to be insulated so there's no cross connect, so the current doesn't short out. So you want the current flowing through that many turns to go from one terminal to the next. Okay, so there's a lot of turns here. So here's the primary, and I'm going to turn on the current here to the primary here in a second. Here's the secondary. So I'm going to turn the current on. You're going to see something happen, but ignore that for the moment. Okay. So now, and here's a current meter. I'm going to back it up so perhaps you can see it better. And I'm going to push the secondary. I'm going to move this over a little bit. Of course, I'm moving things around here. So, all right, now I can start. I'm going to push the secondary towards the primary, and you should see the current flow. As long as I keep pushing it, the current is flowing. And if I pull it back, current flows in the opposite direction. Okay, pushing the secondary primary induces current in the secondary. And I also get an induced current if I pull it back in the opposite direction. Now the second thing is I could push the primary towards the secondary. I get a current, again, in the same direction as when I push the secondary. If I pull it back, I get current going in the opposite direction. I have to keep moving something, right? As long as when I stop moving, the current stops flowing. I have to keep something changing. And the other thing I can do here is to change the current in the secondary. I'm going to turn it off. You see the current flow? Turn it back on. Turn it off. Okay, now let's. I can get these effects to be even more significant by putting some piece of iron. This is a bundle of iron rods, and this simply enhances the strength of the magnetic field. Why that happens, we'll have to discuss. But for now, take it on faith. I guess that the thing is enhancing the strength of the magnetic field. So that should enhance the strength of the effect. So I'm going to increase the current now. There's no current. I'm going to increase the current, and I got a pretty strong response, right? There we go. That's a pretty strong response. Push the secondary towards the primary, pull it away, I get a nice big induced current. Okay. So there's clearly, we talked before about the electric field is required in order to make the currents move, or that is let me back up. That's not what I meant to say. An electric field from a battery in the conductor will cause current charge to move. And we're seeing something that's like that here, but it's magnetic in origin. So it looks like an electric effect, but it's magnetic in origin. It has a different cause. So that's an important thing, an important point to keep in mind. Two things that have the same effect need not be the same because they could be a different cause. If I have I'm in the bowling alley and I knock over 10 pins with my bowling ball, or if I go down and kick them over, right? It's not the same. Same effect, but different cause. I get credit for one. I get score for knocking them over with the ball. I just get people annoyed at me if I kick them over, right? So, two different things. Okay, so, and that's an important thing. In sorting this out, in sorting out cause and effect, you need to be very careful that you don't confuse causes and effects. Just because two causes have the same effect does not mean that they are the same. But we say that in language. You hear people say, in effect, they're the same. You hear that? It went by really quick. In effect, they're the same. Meaning, I'm just going to ignore the cause, the difference, the essential part, which is the cause. I'm going to ignore that and just focus on effect. Okay, but that's unintelligible. That's less intelligible for us. What's more intelligible for us is to understand the cause. Even though the effects are the same, the causes may be different. And that's what happens here in this. There are actually two different causes going on here. Same effect. I get induced current, but actually two different causes. In the first case, I have a V cross B because I'm moving the secondary in the presence of a magnetic field. But in the other two cases, I'm not moving the secondary, and yet I can induce current in it. So these are really two different causes here, and also different from an electric field, right? So I have really three. We're talking about an electric field can cause current in a wire, but also now two different magnetic effects, two different magnetic causes. Okay, the first one here, we have the moving secondary. Now in the primary, there we go, I have a current, and that generates a magnetic field in the plana around it, which extends out to the secondary. When I push the secondary towards the primary, I'm pushing charges. The charged parts of the secondary are now moving in a magnetic field. That causes a V cross B force on those charges, which is in that direction, if they're positive charges. And that causes then an induced secondary, a current in the secondary. Okay, let me go back to that. There's the current is caused in the secondary in that direction. Okay, and clearly if you move them in the other direction, the current flows in the opposite direction. Push the secondary away. Okay, now the other thing is you can move the primary. And the way to understand that is the following. The primary, of course, generates an A field also. Different further specification of the state of the plana. The A field diminishes as it goes away from the wire. How does the A field drop off around the wire? It's logarithmic. Slow, that's a slow drop off, but it still drops off. The A field is weaker, and the direction of the A field is in the direction of the current producing. And at this location here, of course, all of the loop contributes to the A field here, but this is the closest part, and that's what contributes the most strongly. So that's why the A field is in that direction. Okay. And now when I push the primary towards the secondary, look at what happens to the A field at the secondary. That is, for a charge sitting inside the secondary, the A field is increasing. And that induces a current downward in the opposite direction. Okay. That A field, increasing A field causes the charges in the wire to have a downward impetus. It's like they're going in opposite direction. That this increasing A is causing charges to have an impetus in the opposite direction. And that contrary effect, the contrary motion there, contrary induction, is very important, that it goes in the opposite direction. It's called Lentz's law, or it ultimately becomes Lentz's law. It's in the opposite direction. Okay, so what happens then, the way we can understand this, is the plana here, in this vicinity, because the primary is being pushed towards it, the plana there has an increasing A field at this location. It's increasing as the primary is moving towards it. The plana responds to that change in itself, in its state, by finding any charges that are nearby, and it gives them an impetus in the opposite direction. That's how the magnetic induction works. So look at the plana. The plana is the actor here. The plana is the A field in the plana is increasing. And as a result, it looks at any charges nearby and causes a force on them in the opposite direction in proportion to A dot. so that the increased impetus is related to negative A dot. Okay. So the third way is to increase the current in the primary. This is exactly the same, actually. Well, not exactly the same, but this is the same mechanism. Because if I increase the current in the primary, if I increase the current in the primary, again, the plana at this location is seeing an increase in its A field. And the response is to find any charges in the vicinity and push on, give them a force in the opposite direction. Hang on a second, I need to zoom this out so I realize this was not visible. Okay. Okay, so again, the increasing A field, the plana responds by finding charge in the vicinity and pushing down as a result in the direction opposite to the increase in A. That P is not very, that color is not very good, but that's a downward impetus. Yes, sir?
Do we know why that is?
Well, let's go through it, explain exactly what it does first, and then we'll understand more fully why that is. Yes, sir. Mr. McCall.
Could you not look at phenomenon 1 from like the secondary thing?
That's an excellent question. I know where you're going, so let's hold on to that. Okay, because it's a very good question. I want to address it, but let's wait just a minute. Okay, and I'm making a distinction between the first two, and they are different, and you want to know why that is. Okay, so, but let's go through this first. Okay, just so everybody has it in mind what we're getting at here. Okay, there are two causes: the V cross B and the A dot. In the first one, the plana is conditioned to have a magnetic field, and that will cause a force on any charged body that's moving through it because it has impetus and there's a force resulting. The A dot cause, the plana is a different mechanism. The plana which experiences a changing A will cause a force on any charged body moving in contact with it so as to oppose the change. All right, so remember here, two different causes, same effect, but two different causes. They have the same effect, so they are the same. In effect, they are the same. That's an error, right? Don't make that mistake. So the A dot cause, again, just to reiterate what goes on. The plana experiences a change in the A field where it is. It responds by causing a force on any charged bodies in the vicinity. So it kind of compensates for a loss of the A field by giving an impetus in the other direction. So this illustrates the meaning of A as a potential momentum. I'll show you here a little bit more clearly. Again, to illustrate this, it's very similar setup, but just makes it a little bit more clear. Let's just have a current carrying wire has current in it, and I'm going to put a charged body on a bead. So it slides up and down on the wire, a charged bead on a wire. So it can slide up and down this thing. There's no current in this wire. This is the only current that's carrying. This is the only wire that's carrying current there. Okay, now the current there, of course, has an A field associated with it. It generates an A field in the plana. And we're going to, again, if we turn off the current, it drains impetus from the charges. We're draining impetus from the charges in the primary. That reduces the A field. It causes an impetus in the opposite direction in that bead. I'm sorry, in the same direction because we're turning it off. Excuse me, we're turning it off. We're not in the other case we were increasing. Now we're decreasing. So it responds by compensating. It finds charges to give them impetus in that direction. We're draining impetus from here and it responds by finding other charges to give impetus to. Compensates for it. Okay. Now, yes, sir. Mr. Miller.
Next slide.
Yeah.
So when you're decreasing the current, now that charge is moving, so now it's producing an A field.
Well, that's right. Yeah. That's a secondary effect. So
is that where it's trying to compensate because that A field's closer than just the A field going away of the primary?
No, it's got impetus itself, right? That's the compensation.
Yeah.
It lost A field and now has impetus.
So, but the one that it produced is closer to what the first one was producing than the first one just not producing one. So is that why it causes?
No, not exactly. Okay. So just stay simple with me here. Don't try to go too fast. I need to walk through this slowly. Okay. Okay. So now Maxwell made a mistake. As great as he was, he made a mistake. He actually made two. I'm calling them mistakes. They weren't mistakes in a way. right? I mean, what he was doing was confusing causes and effects, though. And so in his formulation of electrodynamics, in order to make a simple, self-contained set of equations, he confused two different causes. So previously, we've been talking about the E field and the electric field as though they were the same. The electric field is the part that's related to the phi field, right? They're related to each other by a gradient. The electric field is the negative gradient of the phi field, the electrostatic phi. Both of them originate from a charge, massive body. Generates a phi and an electric field. Okay, now we saw this A dot effect, though. This A dot term, the force that can be produced because of a changing A field, that's magnetic in origin. What generates an A field? A current generates an A field. That's magnetic. Maxwell is going to incorporate both of them into the E symbol, the E field. It's called E field, but it's not purely electric anymore, even though it's got the E. It's not purely electric. It's a confusion of electric and magnetic. So he's going to put them together, conflate them together into this simple E. The E field, Maxwell's E field, is not purely electric, and that's the confusion. We'll see how he gains some simplicity, mathematical simplicity, by doing this. But the problem is that when you're trying to look for the cause and the effect, it confuses things. It makes it harder to understand what's going on in his electrodynamics. But there's a way out. And the way out, where the confusion is, confusion is cut again, you can restore an understanding, is to follow the A field and the phi field rather than the E field. So that's what we're going to do. And as we go along here, we're going to put more emphasis on phi and A rather than the E field, because the E field is confused. Maxwell's E field, as you see, is a combination of these two. So in other words, you have, in the case where you have an A dot, you have charges in the secondary which are stationary, but which then receive an impetus. Right? Previously, when we talked about magnetic forces, we had to have an impetus, a charged massive body with impetus, could only produce a force in another charged massive body with impetus. Right? We could have two current-carrying wires, like impeti attract, opposite impeti repel, but they both had to have impetus. If one of them didn't have impetus, right, if they're just stationary, in the magnetostatic case, the wires are stationary, then nothing happens. Okay, but now we've got something. If I push the primary towards the secondary, or I change the current in the primary, these charges are not moving, but now they gain an impetus, which is like an electric and so field, right? Because an electric field acts on stationary charges and gives them impetus. So you can see why it's possible to confuse these two things, because they do have the same effect. They act on a stationary charge and cause an impetus in that stationary charge. And so it is like an electric field in effect, right? But it's a magnetic effect. It's a magnetic cause, magnetic in origin. So he's going to put these two together. He's going to write his E symbol as a combination of negative rad phi and negative A dot. And the negative sign is that reverse direction. When A diminishes, it tries to restore, give impetus to something to restore it. Okay. So, but this is truly electric and truly magnetic are combined in one symbol. And there's a reason for doing that, and you'll see why he does that, but the reason for doing it does not really the loss. That is, there's an advantage, but you lose something, and what you lose is very important. Okay, so here's the force then that results. If you write the force in terms of phi and A, and this is on the front cover of the textbook, the force, the complete force for a charged particle in the presence of a phi and an A field, well, there's the negative q rad phi. There's the negative q over c A dot. This is in CGS units, so there's a C appearing here. Negative A dot. And then there's the V cross B, but not written in terms of A, V cross curl of A. The second two terms are truly magnetic in origin. And the first term, the first of the three, is truly electric because it's generated by charges, by bodies with just charge but no impetus, whereas the second two terms, you have to have impetus in the source. generate them. Okay, so let's see. I think I'm going to hold off on this because you're going to do some further reading on Faraday's law. I'm going to hold off on that. And because if you understand the principle here, you can avoid a lot of confusion. Faraday's disk is an example where people get really confused about magnetic induction. And if you pay attention to these principles, you won't get confused in the example of Faraday's disk, right? Okay, now let's see. So I'm going to skip over this part here. Okay, that's good for now. All right, so now I want to go back to the questions. We'll start with Mr. Bacot's question first, and then I know Mr. Dowdle has a question, probably others too, okay? So Mr. Bacot's question, and maybe it's worth reopening what I had here, so let me bring it back here. Very important question, and again, something that we need to make sure that people understand because this is a potential confusion. Okay, I think his question is, because it's a common question, and it's a good one. Aren't these two the same? The first phenomenon is I push the secondary towards the primary, or I push the primary towards the secondary. Aren't those the same? Now, why would you think those? I'm going to put you on the spot. It's a great question, but I'm going to try to tease it out a little bit. Why would you think those are the same?
Because if you looked at them both in the inertial frame of like the secondary being stationary,
right?
they're the same.
So his answer is resorting to relativity. Okay, but remember, so he's saying if we look at it in the inertial frame of the primary, this looks like the secondary is moving, right? Or vice versa. So we change our frame of reference, then we. Okay, so now there's a more complete answer, but the short answer is motion and rest are not the same. The secondary in this first case is at rest, is moving, and the primary is at rest. Right? Or in this case, the secondary is at rest and the primary is moving. Remember when we did special relativity at the end of last term, we demonstrated that what happens in relativity is that the measurements done in one frame can be converted to the measurements done in another frame. And so we could go through a process of calculating A fields and E fields and B fields and stuff in the two different frames, okay? But, and it means that there's no measurement, no process that involves either bowling balls and cannons and pendulas or current loops, things like that, by which you can tell whether, if we take this room, we close off the windows, there's no measurement we can do inside this room that will tell us whether this room is moving or not. Okay, that's the relativity principle that we were working on. Okay, doesn't mean we're not moving. It doesn't mean we are moving or not moving. It just means that we can't do a measurement inside here that will determine that. So, but it's a non sequitur to say that there is no absolute frame of reference. That's not a correct conclusion from that relativity principle. Okay, and that's kind of what's happening in your mind is you're remembering this narrative that there is no absolute frame of reference, and that's not a correct statement. Okay, so now the longer answer, the more complete answer, we have to wait, where we learn how to do the transformations on these fields. Because there is a change in the measurement of the fields from one frame to another, such that all of these things work out to be produce the measurements that are related to each other. Okay, so there's a way of working this out so it's all self-consistent.
So you could view it that way in like a moving inertial frame, but then you have to convert it back to the stationary.
You can do all of your calculations in one frame and predict the measurements, results of measurements, and then you can do all of your calculations in another frame, and those measurements have to be compatible with each other. Okay, but that doesn't mean that motion and rest are the same. They can't be the same. Motion and rest are not the same because there's a change in one and there's not in another. Okay, yes, ma'am.
Would kind of a way to look at it be from the reference point of the plana because there are different causes?
That's the best place to do it. Do it from the point of view of the plana. Exactly right. Mm-hmm. That's right. That would be a really clear way of distinguishing it. Because in one case it's moving with respect to the plana and not in the other. Yeah. Okay. Mr. Dowdle had a question too.
Yeah. This probably is just like, this seems kind of obvious, but like, why can these forces be linearly added? Like, is that just a result of the definition of force?
No, you're asking about the Lorentz Force Law?
Yeah.
Okay, so we're going to get down here.
I mean,
Sorry. This.
yeah. Like,
You're asking why can the electric force be added to the magnetic forces? These two different magnetic forces. Is that your question?
yeah, are there forces that can't be linearly added like that? Or I guess that's just because of force. I think.
No, no. I think your question is important, and it's not, in principle, impossible. In fact, I think in principle you could find situations where those might happen. Okay, but it's observed in practice that these forces superimpose.
Okay.
Just like the forces produced by if I have two charged massive bodies, they produce electric fields, and each produce a force on a third body, and the force produced on that third body is a superposition of the forces that would be present on that. It's empirically observed. It's something that we have to test. It's not in principle necessary, but it is true to great precision and has been tested. Okay. Good questions. Those are all excellent questions, and yeah. So, and we really need to talk about these things to keep things. Okay, Mr. Bicot has another good.
All right, not to go back to this, my question.
Okay, good. Yeah.
Kind of am.
Sure.
If both of them are moving, then would you just pick one and do it from that frame?
You can do it.
Like assuming like the Earth is moving.
Well, you could do it if both of them are moving. If the secondary is moving and the primary is moving, then you would have a superposition here, right? And if the secondary is moving, then this is the speed of the velocity of the secondary, and this is the it doesn't due to the motion of the primary. You would do both. Okay. So in other words, it doesn't matter what frame, as long as it is an inertial frame. This will produce the correct force in that frame of reference. Okay. So in fact, this is relativistic. And that's the thing that wasn't understood in Maxwell's day, because we hadn't really understood relativity yet. Not the full special relativity. There was Galilean relativity. This is fully relativistic. And we're not going to have time to study, unfortunately, but that's taken up in Chapter 7, and it's beautiful. The relativistic nature of the electromagnetic fields is very, very beautiful, how it all works out. Really neat. All of these questions that you're asking, they're really lead to something very important, which is how do the electric and magnetic, how do they sort out between different frames? Because in one frame I might have charges are stationary, in another frame they're moving. So in that other frame I should see a magnetic field produced by these moving charges. Whereas in the first frame I see only an electric field. So there's clearly a connection here. And this is a very important thing to sort out, but you have to go slow. You have to take your time. And you can't make mistakes. I mean, you should not make mistakes like Maxwell was doing by conflating these two different causes. That'll confuse you later as you go through things. That will cause confusion later. What happens then when you do this, as Maxwell has done, it results in a compact set of equations, but then you lose the physical connection, the physical understanding, the cause and effect gets lost. And so what happens in that case is we replace that physical understanding with a narrative, a recipe for calculating things. You just calculate stuff this way, and it all comes out, right? That's the narrative. You can't really understand this stuff. Just calculate stuff, and it'll all work out. And it's a crutch. It's great. It's successful. You can calculate stuff, but the crutch is that you no longer challenge yourself to understand what's going on because you're satisfied that I can calculate. And then I can explain, and the understanding of the experiments comes down to just doing a calculation. Well, here the equations say that it should do that. So that's enough, isn't it? It's not enough. It should never be enough for us. Okay, so that's why this is so important. And this is an example. Maxwell was a genius. I mean, there's no discredit to him. He accomplished a huge amount, but the priority that he had at the time was to try to find a compact set of equations to describe electric and magnetic effects together and part of the price he paid for that and doing it the way he chose to do it was that he disconnected some from the cause from the effect. And he's focusing on effects, not causes. It's very much like what Newton did, focusing on effects, not causes. So, but that makes it less intelligible to us. Okay, yes, sir, Mr. Dowd.
So is the E field and the B field, or the phi and A, which one's the more primary thing?
Yeah, that's a very good question, and I think the jury is still out. But this and other evidence is mounting that he discusses in the book, which you may not fully understand. But there's mounting evidence that phi and A are more fundamental than E and B in some way. It used to be when I was a student that phi and A were mathematical devices, just conveniences. You just use them in order to, because it's easier to calculate things with them. But you go back to the E and B when you really want to understand things. That was the story. I think the evidence is building in the opposite direction. There's a lot that is physical about phi and A. Okay, so to give you some of that, there's two bits of evidence aside from this that come from more advanced physics that you haven't done yet. If I take a solenoid like this, if I make it a long solenoid, and I take an electron beam, and I split the beam and pass half of it on one side, half on the other side, and bring it back together on the other side. Now you remember, in the solenoid, if I have a nice solenoid, there's no B field outside, but there is an A field. Okay? Here's the interesting part. When I recombine the electron beam, I can control the current on the far side by changing the current, that is the intensity of the electrons coming out on the other side. I can control that by changing the current in the solenoid. But the two electron beams do not see a B field anywhere. They see only an A field. That's called the Urraco effect. And it was actually predicted before it was measured by David Bohm and I've forgotten his first name, Urraco, who was emeritus faculty at USC, actually down in Columbia. They predicted that before it was observed, and now it's been observed very clearly. It's very, very clearly an effect going on. And it seems to indicate, at least just naively, that there is an A field is producing a physical effect on the beam when there's no B field around. So the A field has something real about it. Okay, so that's a very interesting thing. The second thing is if you get to the more advanced graduate level courses, you're going to do quantum electrodynamics. So you're going to take electromagnetism and do the quantum version of it, QED. Quantum electrodynamics is always done in terms of phi and A, never E and B. It's a mess. In fact, I don't know if there's a consistent way of doing it with E and B, but phi and A is very simple, relatively simple. It's very clear, cut, know how to do it, no problem. Okay, and it's clear in that, in fact, that the understanding of A as a potential momentum comes into the formulation of quantum electrodynamics because the coupling between the momentum is to the A field. The A field couples to the momentum of a particle, and in such a way that there's a conservation law that's based on the combination of the two. Right? If A goes away, P builds up, and that's built into the quantum electrodynamics in the coupling. So those two bits of evidence, and some more really, that's mounting, is much stronger argument for the reality of phi and A, that there's a real physical nature to these fields that have some physical effects that are, we can observe. So we take it much more seriously now than we used to when I was a student. They were just mathematical devices. Now I think there's a lot stronger evidence that there's more to it than that. It's really very interesting. Okay, now let's go back to the case of, let's go back here to this case. Say, let's see, here, where I push the secondary towards the primary, let's take an example. And now I've got a current induced in the secondary. Now here's a secondary effect, meaning that the secondary now has a current. It's producing an A field. Okay, let's look at what's going on. The A field that's been induced is producing an A field back in the vicinity of the primary that it didn't have before. What's going to happen?
Current's going to change.
Yeah, well, there's a couple of things. One is we have two currents. Are they like or opposite? They're opposite. Opposite impeti repel. So these two current loops are going to have a force, produce a force, one against the other. It's going to resist this. You know, you're pushing one towards the other one. If the primary were not nailed down, it would start sliding away. These are too heavy to demonstrate that, right? If you push the secondary towards the secondary's got no current in it, but the current is induced, and it's going to push the primary away. That's a secondary effect, but it's a mutual induction that's going on. The primary induced the current in the secondary. Now the secondary is causing a force, and in fact is also doing some back induction on the primary. So that it really gets kind of complicated here. We have all these effects going on. Yes, sir.
Now, in
Mr. Coulter.
a case like that, so it induces the current in the opposite direction in the secondary.
Yeah.
Would it also send back, would it amplify the current in the?
Yeah. Which way does it go? Okay. So the current now.
It would produce a current in the opposite direction, which would, because they're moving together, it would cause a current.
The A field is going in an increasing A field in the downward direction would try to enhance the current in the primary. I think that's right.
Would it cause a feedback system or no?
It is a kind of a feedback, yes. But yeah. Mr. Bicot.
So the secondary would slow down?
Well, it depends on how you're moving it, right? If it's just moving freely, you've given it some impetus, and there's nobody pushing it, then it would slow down, right? It would see a back force on it, and that's to reduce its impetus, right? As a result of this induction. So, well, it even gets more complicated. Not more complicated. It even gets more interesting than that, because a single current loop, if it has no current in it, if I turn the current on now, there's actually a self-induction that's going on that will tend to resist the current turning on, and that's an inductor. And you're going to look at this. So there's both mutual inductance, which is what we're talking about here, but there's also a self-inductance. Okay, so it's really kind of interesting. It's very rich effect. A lot of things to tease out here, but you got to go slow. Don't jump into this too fast. You got to go slow, because you want to remember the process of abstraction. You can take something out, consider this, and then try to put it back in connection with the other things. So we go slow, build up our understanding. Okay, so that repulsive interaction. Let's suppose we take a magnet. I'm going to drop it into a copper pipe. We're going to do this demonstration on Monday, but your homework asks this question. What would happen if you dropped the magnet down a copper pipe? Has anybody seen that demonstration? Yeah. What happens?
It goes very slowly.
It takes a long time to get to the bottom. Right? If this were a plastic pipe, or if it weren't a magnet, it would just drop like things normally drop. But if you drop a magnet inside of a metal, a conducting pipe, it's very slow. So what's going on there? It's a magnetic induction. And a student last year made this nice illustration to help you understand what goes on. So I'm going to turn this on for a bit here. Okay, so remember, what we're treating a magnet as a wire loop because we can understand that better. A natural magnet is a little bit strange because we don't have a clear understanding of how that produces a magnetic field. So let's just consider dropping a wire loop, and the loop has to be oriented so it won't flip, right, while it's dropping down. So you have to make this. If you're going to actually make it with a wire loop rather than a magnet, you'd have to constrain it somehow so it doesn't flip over. But you could do it with a wire loop in principle. It's just easier to do with a magnet because you take a cylindrical magnet and drop it inside of a pipe. Okay, so notice what's going on down here is the wire loop comes down. There's an A field in that direction. And at this location in the pipe, the A field is increasing, right, when you're below the loop. So what does that do? A field is increasing. So which way? There's an induced current because of the A dot in the opposite direction. All right, so below in the wall of the pipe, below the magnet, there is an induced current. Below the current loop, there's an induced current, opposite direction. Okay, what happens then? If there's an induced current, what happens?
There's a force.
Yeah, there's a force produced on the wire loop. Which way is it? It's repulsive because they're opposite. Okay, so that force is opposing gravity, pushes up. It resists the fall of the loop. And the strength of that force is proportional to the rate of drop of the loop, right? Because it's an A dot effect, depends on the rate. So the strength of that force depends on the rate at which it's falling, because that's what determines how fast A changes. Okay, now consider what's going on above the loop in the piece of the cylinder above where the loop has already gone. Okay, so it's up here. What's happening here? What's happening to the A field in that piece?
They're also producing.
Yeah, but what's happening to the A field?
It's in the same direction.
It's decreasing, right? The A field is in the same direction, but it's diminishing, right? It reaches a maximum when the loop is there, in that part. So that when the loop falls through, the A field first builds up, then it starts to decrease, right? So now we're in the decreasing part. The A field's in the same direction as it was before. It's just diminishing in its intensity. Okay, so which way is the current going to flow?
This right. The same way as.
Same way as the wire loop now, right? Because the A is decreasing. A dot's in the other direction. So the induced current above is in the same direction as the wire loop. So we had below, it's in the opposite direction. Above, it's in the same direction. Okay, now they're the same direction. They're attractive. Another force that's also in the up direction. The two forces together both oppose gravity. They're in the same direction. One of them because the A field is increasing down here, the other one because it's decreasing in half, and because it works out that way. Both of them work together to produce a force on the wire loop that opposes gravity. And remember, the strength of that force depends on the speed with which it is falling. The faster it falls, the stronger that force. So at first, it's as it's just getting into the pipe, but even though it's still accelerating, right? It's gaining impetus because of gravity. And so this opposing force is starting to build up. But now it gets to the point where they balance. And so that balance is when this induced force is exactly equal to the gravity, and it's a uniform linear translation. The induced force balances gravity. There's no net force on the thing, so it just drops at a uniform rate. Okay, so we'll do that demonstration in class on Monday. If you try to ask somebody who doesn't know the A dot to explain this, they might break their arm, because they get into all these right-hand rules and stuff. Just try it. Ask somebody who doesn't know just the V cross B and all that stuff, the normal way of explaining magnetic induction. I can do this sitting in a chair, and I don't even have to use my arms much. I can do this. That's about it. But if you ask somebody who doesn't know the A dot, the understanding of the A dot, they'll have to get out of their chair and have to do stuff like this. It's kind of amusing to watch. See, I make it safer for you to live now. Okay, so let's see. The other one was the can crusher. That was the other question that you dealt with. So let me pull up the can crusher. Let's pull up the my note device here. In the ring launcher, those are all different things you can do with magnetic induction, demonstrations of magnetic induction. Let's look at the ring at a ring launcher. Let's suppose I have a washer, a metallic washer, and I put it on top of a solenoid like this, and I might want to help guide it. I might want to put a rod to help steer the ring a little bit. If I start off with no current anywhere, and then suddenly I load current into the solenoid, what's going to happen to the ring? It's going to pop up. And it doesn't matter which way you push the current. Current could go in either direction. It's going to pop the ring up. And again, you can understand that. What's happening?
Generating an A field.
An increasing A field in the washer, and that induces a current in the opposite direction, and they're opposing forces, and the solenoid is held in place, so it pops the ring off. It's a nice little demonstration of magnetic induction. The other one is the can crusher, which is a little unsafe to do, and I've actually not asked Jerry to do it this year, but it's quite a demonstration. In this one, you want to increase the current quickly, right, in the ring launcher, and that's the trick. How do you dump a lot of current into something quickly? And usually you have a capacitor that's charged, and so you have to have a pretty hefty capacitor, which means that there's potential of injuring yourself or somebody else. You have to be really careful about how to do this. So he's got this really massive capacitor that he uses, and he'll have kind of a, it's really not much of a solenoid. I guess we could increase the solenoid here. We have an aluminum can that's inside here, and you dump the you charge the capacitor up. It takes about an hour to get a good charge on it, so you really only have one shot to get it right. And you want to insulate the can from the solenoid, right? So there's a plastic sleeve in between the two that I won't draw here, but you don't want current flowing crosstalk in this. You just want current, you don't want current that you put into the solenoid. You don't want that directly going into the can. You want the induced current in the can. So you dump this current into the solenoid. You get induced current in the opposite direction. What happens to the can? Yeah, it implodes. It can even rip it apart. The aluminum is not really very strong. It will neck down, and even in some cases just rip it apart. But it makes a big pop because there's a spark when you throw the switch. The switch sparks, so you get this great big flash and pop as well. And the can goes flying off. It's pretty good. Okay, questions? Okay, so you're going to be considering now the form that's called Lenz's law and Faraday's law of induction, and but you have to be kind of careful here. And he's going to walk you through something that really confuses a lot of people, and that's Faraday's disk. Faraday's disk is the following: you have a magnetic disk in a magnetic field, a metal disk. Excuse me, a metal disk on an axle. So you have a crank. You can turn this thing like turning a wheel. You put it inside of a magnetic field that's perpendicular to this. So you could put say a U-shaped magnet like this with north and south poles like that. Go around it like that. So and it puts a magnetic field, and then you can hook a circuit up here that connects. On one end, it's touching the rim of the wheel, and the other end is touching the center of the wheel. And then you have a current meter here. You can actually get current flowing from this. Why does that happen? And to understand, this has confused a lot of people. But if you follow the charges, then you'll understand what's going on. Follow the charges and go back to the phi and A dot and V cross curl of A. Follow those through. Follow how the charges are moving in this. They must be moving, in this case, radially like that. Follow those, and then you'll understand how it works. This has confused a lot of people. But if you use the A field, you don't need to be confused. Okay. And the A dot and the V cross B. If you keep those in mind, the V cross curl of A, you'll be all right. So that's Faraday's disk. And there's another example. Faraday's disk is in Feynman's E&M book, and he's obviously intrigued by it. And there's another one that involves something similar to rocking. As I recall, it's See, I'm not sure I'm recalling this correct, but it's an odd-shaped, pie-shaped thing that's rocking in the presence of a magnetic field, and it's potentially very confusing. But if you just do what I said, remember the fundamental principles here. The phi and the A produce force in the way that we talked about, and follow the charges that are moving in the conductor, then you won't get confused. You'll get the right answer. Okay, so see you Monday.